Okay, so good evening everyone. So yeah, this is the fifth live session for the NPTEL course Chemical Process Intensification, and the topic that was discussed during this week in the week's course was optimization for process intensification. So in this week, basically what Professor Majumder sir has discussed is how to perform optimization, and what is he has first discussed that okay, what is optimization and what are the different algorithms available for optimization, for specifically for designing a chemical process. Then specifically for process intensification, what are the available algorithms are there, and he has extensively discussed over many algorithms. Then after that he has also performed one case study using one of the paper by Sarkik and Gu from 1994. So and yeah, so let us start with the today's live session. So what is optimization? So optimization are a series of techniques, and where you a series of mathematical calculation and a series of steps that you perform to basically achieve to a certain goal, and that goal is to maximize or minimize a certain objective function which represents a measurable quantity that needs to be optimized. So that is what an optimization, the definition of optimization is. That the goal of optimization is to maximize or minimize a certain objective function which represents a measurable quantity that needs to be optimized. So for an example, your objective function could be that okay, capital costs to set up an plant, or a particular to make a process running, a certain capital cost is required. So here your objective function most likely will be to minimize the capital cost. So if you are able to minimize the capital cost, your you will basically you will optimize your process. And in another way, in another scenario, what might happen is your objective function would be to basically to maximize the yield of a particular process. So in that manner, you may go for basically increased specific volume, or you install more reactors, and you may use more amount of raw materials to maximize your yield. So that might be your goal. So these are some of the example of objective function which we will further discuss more, but yeah, so the goal can be to maximize or minimize a certain objective function. It is not always that you will aim to maximize a certain thing. So in some cases it would be better that okay, you focus on minimizing a certain quantity. So this can involve maximizing profits, minimizing costs, achieving the highest performance, or finding the optimal configuration for a given problem. So these are the examples of objective function that okay, you can aim. Your objective function could be profits, or your objective function could be capital costs, or your objective function could be performance. So there you might be interested in to maximize the profit as an objective function, and you might be interested in minimizing the cost, capital cost, as an objective function, and there you might be interested with achieving or maximizing the performance of a given process as an objective function for finding the optimal configuration of your given problem. So mathematically it may give you certain choices that okay, these are the certain choices that are available for a given process, and you must choose from those available choices to basically optimally run your process. So performing an optimization calculation would result in, so you input certain data or you input certain heuristic model and you input your expectation, your objective function, what you want to do, and based upon that you would get certain choices, mathematically defined choices, and certain range of choices that you might choose for optimally running your process. The mathematical model for the objective function allows for the comparison of the different choices for determining which might be the best choice for the optimal design of the process. So once you are able to get a certain range of choices, now you can perform further optimization study to basically identify what is the most optimal choice available to you. So your target would be to hit that mark such that your plant is running on an optimal mode. So this mathematical exercise that you perform, this optimization process over an objective function, would give you the best choice to the best conditions to operate your plant such that your plant is running on an optimal mode. So that is the advantage, or that is the result of the optimization calculation. Now some examples. So some examples could be that, okay, in the process model building stage, the optimization problem is global and multi-objective optimization problem. So your optimization problem on a process building stage is global in nature. It's not that you are focusing on a local point, but on a global model. On the whole model, your goal is to perform the optimization process on the whole model, process model itself. And there you will usually find that the objective function is not only single objective function, there are multiple objective functions. Like we discussed that, okay, your one of the objectives might be to maximize profit, and another objective would be to cut on the capital costs, to cut on the amount of raw material used, and to another objective would be to increase in yield. So here the process model building stage, the optimization problem is global in scale and is a multi-objective optimization problem. Now for an example, the parameter identification in thermodynamic and kinetic models, and this involves performing phase equilibrium calculations. Now the another example would be coming under process design and synthesis stage. Here also the optimization problem is global in nature and is a multi-objective optimization problem. So here the example, a good example would be heat exchanger network design. And another example of optimization comes under the stage of process operation stage, where the optimization problem is again global in nature and is a multi-objective optimization problem. For an example, scheduling batch plants and managing supply chains. Now, if you see, traditionally, optimization problems in chemical engineering have been handled using a single objective function. So in chemical engineering, what has, for a since very long time has been happening is that engineers take a single, they mathematically define a single objective function and then solve for it and optimize the process using that single objective function. But that is not the case in real life system. How long can you go on with a single objective function? I mean, in the real life, the chemical processes are always a multi-objective function problems. So that single objective function is generally associated to an attribute or characteristic to be minimized or maximized for the system under analysis. So this type of optimization problems encourage the development of novel and powerful numerical strategies. No doubt the real chemical process process plant is a multi-objective problem, but the previous engineers had to start somewhere. So they started by optimizing the process using a single objective function, and that led to the development of novel and powerful numerical strategies. But nowadays it is not the case that you can apply a single optimization function to design the process, to optimally design the process. So nowadays the design of the chemical process must consider different objectives simultaneously, and so in today's world, in today's this era of high computational, high performance computing, HPC, you should not be limited to just consider only single objective function. Your chemical process design must also consider the optimization problem as a multi-objective optimization problem. And there basically the idea behind that is you should consider also the energy consumption as an objective function, environmental impact as an objective function, social impact as an objective function, and among the others may involve your profit and your yield. So it is so the chemical processes, when you are trying to optimize, you should consider them as a multi-objective optimization problem. So actually the optimization in chemical engineering is mainly focused on the solving of various parallel single optimization problem. So you should be not parallel but a combination of serial and parallel single optimization problems. So it is a combination of that. Now, considerations of simultaneous effect of environment, social and sustainability aspects make the chemical process synthesis a more complex problem. So the chemical processes are inherently a very complex problem. So why they are complex? Because they consider the simultaneous effect of the environment, social and sustainability aspects. So that's why they are quite complex, and such complex system to perform optimization, to perform process intensification for such chemical processes is a very challenging task, because the system is inherently quite a complex system. So to have an optimal solution, different criteria must be considered simultaneously based on those effects. So you must account for each of those effects. So you can take some assumptions that okay, certain effect is quite negligible, so to save the computational time, and yeah, you can say that okay, we have assumed so and so, but that should not happen so in such a scale that you completely ignore the very crucial aspects of the problem. So you must account for each of the significant effects and account them in your mathematical problem as individual objective functions. So again, the limitation with the single objective function towards the chemical processes design in today's era is that the chemical processes are usually multi-objective in nature. So you cannot apply a single objective function optimization technique to it. So it should be a multi-objective problem optimization technique, and normally there are several objectives in conflict between them. So in real world, when you try to design, where you will observe is there are several objective functions in the chemical process design that would be conflicting in nature. So on one hand, you might be interested in getting more amount of yield, but at the same time your interest is to reduce the amount of raw material utilized. So there comes a dilemma that okay, if I use a less amount of raw material, I might be able to make better profit, but then I also have to make the market demands. I have to also fulfill the market demand. So I need to keep up with the market demand, and market demand is rising day by day. So you need to produce more. So how will you produce more if you are using your raw material less? So these are some of the conflictive objective functions. So that is why the optimization problem in real chemical system is quite complex, because of several objective functions, and that too they are conflicting among themselves. So these conflicts are restrained to the requirements, physical or economical limitations. So this sort of conflicts are actually limited, are actually requirement limited. So now such as the physical or economical limitation, like for example I just said that okay, if you want to increase your profits, so that comes under an economical limitation. And there can be another limitation, physical limitation, that your land area for setting up the plant is limited. You cannot go and extend or purchase another land to expand your plant. So the only way could be that okay, you have to increase your amount of raw material used, and that to sacrificing, not sacrificing but sticking to the same amount of residence time. So you cannot increase your plant volume, but so yeah, you have, so this comes under physical limitation. So generally what happens is this sort of conflicts among the objective functions arise most commonly due to the physical or economical limitations. Now let us go to the optimization methods. So what are the different methods that are available to perform optimization for the chemical process design? The most commonly or the broadly available two different approaches that are used in optimization are deterministic methods and stochastic methods. So all of the optimization techniques can be broadly classified into two different approaches. Those are deterministic methods and stochastic optimization methods. They include the algorithms with local and global convergence properties for handling one or several objective functions simultaneously. So these methods, they include many different algorithms which are capable of handling multiple objective optimization problem, multi-objective optimization problem, and that too with local and global convergence also. So now based upon what you want, you may choose one of these two methods. So if you are very keen on targeting very specific numbers, then you might go with the deterministic methods, where you would solve the complete entire where you would model the system using starting from the basic fundamental approach. Like you would start to solve using the conservation equation, mass conservation equation, momentum conservation equation, species balance equation, and temperature conservation equation, energy conservation equation, sorry. So that those come under the deterministic method, where you start to model your system to perform the optimization from the basic fundamental sciences. So those come under the deterministic method, where you are targeting to get some very specific numbers. Other than that, the stochastic methods rely on probability a lot. They involve heuristics, certain axioms, certain assumptions, and certain models, and which model works better for you. So those are quite probabilistic in nature, but they are quite easy to solve, and they are computationally cheap to solve. So yeah, so these two methods include various algorithms with local and global convergent properties to handle one or several objective functions simultaneously. Now these optimization tools may vary significantly depending on the problem at hand, based on the following parameters. So the optimization algorithms or the optimization tools that are available in each of these methods may vary significantly based upon the depending on the problem at hand and what are the parameters that are focused. So the parameters that are in focus to which you want to optimize to which you want the system to be optimized for is The parameters are the characteristics of the system, the convergent properties of the algorithm, the capabilities of the algorithm, and the limitations of the algorithm. So each of the algorithm will have certain characteristics associated to it, certain convergent properties associated to it, certain capabilities associated to it, and certain limitations associated to it. So each of those algorithms might be capable to account for certain property or certain targeted objective function that you might be interested in. So that those things, come under the capabilities of the algorithm. And there might be certain limitations also that you might want to avoid. So certain algorithm you will avoid because of the limitation it poses, and you do not want to include in your study such limitations. So choose correctly, choose wisely what sort of algorithm you want to use to perform the optimization for your chemical process plant. So coming under the deterministic method, the deterministic methods search systematically for optimum value within the prescribed range of the decision variables. So again, yeah, as I told, the deterministic methods are quite computationally intensive. Why? Because they go systematically. They go by basic fundamentals. So they search systematically for the optimum value within the prescribed range of the decision variables. This method may offer theoretical and computational guarantees to find optimal solution. So deterministic method is guaranteed to give you a theoretical and is theoretically and computationally guaranteed to give you an optimal solution, but at the cost of high performance requirement in terms of computational power. So high resource utilization is to be there, but what you would get is a very guarantee of hitting a certain optimal solution for a given process. For the deterministic algorithms, an exact knowledge of the behavior of the objective function is required, as they are based on the gradient information. So again, as I was saying, that okay, for deterministic algorithms, an exact knowledge of the behavior of the objective function is required. So you start your objective function, let us say if you want to increase the intensify the mass transfer or to optimize the mass transfer. So mass transfer is basically dependent upon the how the species is getting transferred. So your fundamental starting from the basic science, you will question that okay, how my concentration of the given species is behaving. So for that you might then solve the species conservation equation. So there you go. So there you need exact knowledge of the behavior of the objective function. Your objective function is to basically optimize the mass transfer. If in case, then you will basically solve the species conservation equations, because you are interested in how much of your concentration of the species is getting transferred or is getting transported. So there your exact knowledge that okay, if your flow is in the Stokesian Stokes regime, so there because the convection is not a dominating phenomena, so your entire mass transfer will be dominated, will be diffusion limited. So you might then simplify your system by basically cancelling out certain terms, inertial terms in the species conservation equation. So thereby, if you have an exact knowledge of the behavior of the system, of the objective function of the system, for example the concentration, then you can basically simplify your computational model also to basically save time and computational resources. Now common deterministic optimization methods include linear and non-linear programming, integer programming, dynamic programming, and gradient descent. So these are some of the common deterministic optimization methods. Now coming to the stochastic methods. So the stochastic methods have an outstanding performance and offer several advantages for solving problems in process intensification. The stochastic method employ a random search and heuristics to find the solution of the optimization problem. The stochastic methods are designed to handle uncertainty and randomness in optimization problem. They account for the variability of the input data and model parameters by incorporating probability distributions. So the various stochastic methods include Monte Carlo simulation, evolutionary algorithms, simulated annealing, Markov chain Monte Carlo. Now the advantages of, we would be discussing each of these stochastic methods, but let us first discuss what are the advantages of the stochastic method, because we have explicitly said that okay, stochastic methods have an advantage over the deterministic method, but not always the case, but yeah. So the advantage of those stochastic methods include that they do not require any sort of assumptions for the problem at hand. They are capable of addressing the non-linearity and non-convexity of the objective function as a black box problem. They are relatively easier to program and implement. Most of these methods have their extrapolation to multi-objective optimization. They are easy to parallelize to efficiently handle large-scale optimization problem. They significantly reduce the optimization time, especially for the problems with several decision variables. So these are some of the definition of the optimization stochastic methods. We will be coming back to what are the different stochastic method available, different algorithms available under the stochastic method, but let us first define mathematically an optimization function. So what does an optimization problem looks like mathematically? So mathematically, the optimization single or multi-objective problem involved in the process intensification can be defined in general as follow. So this is the mathematical definition of an optimization problem in process intensification. So you can see that it optimize the function. The goal here is to optimize, and there are different multiple objective functions in the square bracket. Now those that optimize can mean minimize or maximize. So that's why instead of writing minimize or maximize, I've written optimize. But generally in the whenever you have performed linear, whenever you have studied linear programming in your mathematics, so there you might have seen that okay, the objective function is the keyword associated with the objective function is to maximize or minimize. But here, as there are multiple objective functions, so one might be to maximize and one might be to minimize. So based upon what objective function you are trying to target, your optimize function can be minimize or to maximize a given objective function. So this here in the square bracket is a vector of capital F, which includes in its element as multiple objectives in multiple individual objective functions. So that makes up the vector capital F. And those several individual objective function are a function of the constraints, not the constraint but the variables, which is also again a vector of several variables of several n number of variables. So x1, x2, x3 till xn, and these variables are having a lower limit of xl and an upper limit of xu. So this is the mathematical definition of an objective of an optimization problem. So where the k is the number of objective functions, so f of k is the number of objective functions involved, and x is the vector. X is a vector that includes several of the component x variables, n number of x variables with lower xl bound and upper xu bound. So the objective functions are a subject to m number of inequality constants that you should be solving your objective function, solving for your objective function above a certain inequality constraint, that okay, or below certain inequality constraint. So basically you should not be lying in that range. So that is the idea behind the inequality constraints and certain equality constraints, that your model for the process must hit certain equality constant, that okay, your objective function should pass through such that this equality is satisfied. So those are certain equality constraints and certain inequality constraints. So the objective is to determine from among this set of all the vectors the particular set of values x1 star, x2 star and xn star till xn star that yields the optimum value for all the objective function. So given the inequality constraint, given the equality constraints for a vector of objective functions that constitute a given optimization problem, the goal is to identify the optimal values for the variable x1, x2, x3 till xn, such that your optimization various objective function are able to perform in an optimal manner subject to such inequality and equality constraints. So that is the idea behind the mathematical definition of an optimization function. So the objective functions involved in the optimization of chemical processes are generally indicators of their characteristics, operation and performance. So, and they can be related to different metrics, including the process effectiveness, economic indicators, environmental impact, safety and reliability, control properties, other attributes such as the characteristics of interest to be improved or to analyze, and including any sort of combination between them. So what can serve as an objective function in a chemical process design is one of the example is process effectiveness, certain economic indicators, what is the environmental impact by your chemical process, what is the level of safety and reliability of your chemical process, and what are the control properties associated to your chemical process. And then there could be other attributes involved as well, but these are on an overall basis can come as the objective function for the intensification or optimization and intensification of a chemical process. For the case of the process model building, these objective functions can be related to the thermodynamics calculation or parameter identification problems. So again, this optimization problem is not alone. This can be basically associated with related or associated with the thermodynamics calculation or parameter identification problems. Now, if the problem associated with only one objective function is to be optimized, so if you have a chemical process where you define a mathematical problem and that problem consists of only one objective function, now if the problem associated, if the chemical process has the, if the problem that is associated with the chemical process is consisting of only one objective function to be optimized, then again it is a single optimization problem, not a multi-objective function optimization problem. And this optimization problem can be classified in subfields depending upon the characteristics of the objective functions that are involved and type of the decision variables involved and the constraints that you are setting upon your variables that are involved in defining the objective function. So in this regard, the target is to identify the set of values for the decision variables that provide the global maximum or minimum value of the objective function used. And if two or more objective functions are involved in your chemical process design, so then again it becomes a multi-objective function problem, objective function optimization problem, and then the problem is handled as a multi-objective optimization problem. And in this case, the objectives are in conflict between them. So then in such case, there exists a simple solution is not describable. You cannot describe a very simple solution if the multiple objective functions are in conflict among them. So, and in certain cases you might also be getting some solution to that optimization problem which may not be even feasible. So for this kind of problem, a set of optimal solutions would be coming up, and those set of optimal solution may represent certain trade-off among different objective functions. So instead of, because in the case of single objective function optimization problem, you were getting a single solution, but in case of multi-objective optimization problem, you might get a set of optimal solution, some of which out of which some of them may not even be feasible, and some of them basically would represent certain trade-off between different objective function. So there comes that, okay, so there comes the concept of Pareto front, that okay, that certain set of solution, that set of optimal design solutions that are achievable, they are defined by means of Pareto front, which is a set of optimal non-dominated solution. Now this Pareto front allows having not just only one optimal solution, but a set of optimal solution that represents the best compromises between different objective functions in consideration of a given optimization problem. So what is a Pareto front? The Pareto front refers to a set of solutions that represent the best possible outcome for multiple conflicting objectives. A vector for decision variables x star, which is an element of the entire optimization problem f, which is again consisting of multiple objective functions. So this capital F is the vector which consists of multiple objective functions, and where those individual objective functions are a function of x variable. And there the Pareto front will again represent a subset of those vectors, where these objective function would be again dependent upon the x star values, where these x star values represent the optimal solution, or they represent the Pareto optimal if there does not exist any other x for given element of f, such that certain given objective function for any x value other than x star should be less than or equal to of that. And the function again, it should be less than the f star. It should not happen that it becomes equal. So yeah, where the x star is the Pareto optimal if there is no feasible vector of the decision variable x, which is an element of the f set vector. This set of Pareto optimal is called as the Pareto front. So this set of Pareto optimal of a given set of the objective functions, and if you take the as a whole, is called as the Pareto front. So whenever you are working on a software program, like S-Pen, so there you might be interested in getting the Pareto front of a given problem. So there the computational model will again perform the optimization, compute the optimization problem for you based upon whatever algorithm that you might choose, and based upon that and based upon that you might be able to get a certain Pareto, a certain optimal solution. Those are called as the Pareto front. The optimization variables used for the intensification of chemical processes are degrees of freedom related to the operation, configuration, and physical characteristics of the system under analysis. These variables can be discrete and continuous. Now, traditionally, the objective functions involved in the intensification of chemical engineering processes are highly nonlinear, multivariable, and potentially non-convex. Highly nonlinear, multivariable, and potentially non-convex. The complexity and the difficulty of solving optimization problems, including the analysis of their solutions, are likely to increase with the number of the objective functions considered. So as your complexity increases, your number of objective functions are bound to increase. So yeah, the complexity increases, your objective function to which you want to optimize individually, they should also increase. Now, types of stochastic algorithms. Now, broadly, there are two types of stochastic algorithm. So we have seen deterministic methods and we have seen the stochastic methods. Now, focusing on the stochastic methods only, because deterministic methods involve heavy computation and those involve identifying or having a basic understanding of the fundamental of the system. So here we cover only the stochastic algorithm, and so broadly there are two types of stochastic algorithm. So broadly there are two types of stochastic algorithms, called as evolutionary algorithms and classical algorithm. The evolutionary algorithms are a family of optimization techniques inspired by the process of natural evolution. Evolutionary algorithms are powerful tool to tackle mono and multi-objective problems which are based on an imitation of evolutionary principle of nature to reach optimal solutions through a population of potential solutions over the successive generation. Evolutionary algorithms are particularly useful for the problems with multiple objectives, non-linear relationships, and when the solution space is too large and also poorly understood. So yeah, those are the idea behind the evolutionary algorithm. That the basic idea behind that is that it is inspired from the process of natural evolution. So you will first identify a certain solution, optimal solution, from a set of potential solution, and thereby you reach the optimal solution via successive generation by performing certain by applying certain algorithm to it that will perform the computational task, and again that will give you that will show you that okay, what are the optimal solution available for a given set of potential solution. Now, the evolutionary algorithms have been used to solve different problems, to solve complex problem in industry and services area, and also in the areas ranging from the finance to production management, and also in engineering and research. The problems consider single and multiple objectives with constraint in most of the cases. Now, what are the steps for the evolutionary algorithm? An evolutionary algorithm contains following overall steps. So, an evolutionary algorithm consists of initiation, selection, termination, crossover, and mutation. So, these 5 steps of initiation, selection, termination, crossover, and mutation, these steps each correspond roughly to a particular facet of the natural selection, and provide easy way to modularize implementation of this algorithm category. Now, what are the differences between the evolutionary algorithms and between the classical methods? So, the evolutionary algorithm considers a set of solution instead of a single one. So, the classical method, when you apply classical methods to an optimization problem, you would get a very single optimized solution. But evolutionary algorithm, when you apply classical methods to an optimization problem, you might take only single potential solution and then verify whether it would work or not. But in evolutionary algorithm, it is not the case. In evolutionary algorithm, you initialize your algorithm with a set of solution, set of potential solution instead of a single one. Now, in the evolutionary algorithm, the generation of the Pareto can be done. So, in order to generate the Pareto front, basically the set of optimized solution, the classical method addresses the multi-objective problem, making a single objective problem. So, the classical methods, they somehow, using certain assumptions and certain mathematical formulation and modeling, what they do is they model the multi-objective problem, the multi-objective system as a single objective system, mathematical problem, and then they generate the Pareto. But such is not the case with the evolutionary algorithm. There you generate a Pareto by considering the problem as a multi-objective optimization problem. So, what are the approaches for the classical methods? Classical algorithm. The approaches for classical algorithm, there are two approaches for classical methods. One approach is to consider the optimization of an objective, while the rest of them are treated as restrictions. The other approach is by performing a weighted sum of the different objectives by grouping them into a single function. So, the approaches for the classical methods, it involves So before we discuss why evolutionary methods are much more suitable, we were discussing about what are the basically the limitation, and so we would go the limitations for the classical methods. And to first before discussing that, we were discussing that okay, what is classical method and what are the approaches for classical methods. So there are two approaches for classical method. One approach is to consider the optimization of an objective, while the rest of them are treated as restrictions. So if you have a multi-objective optimization problem, one approach to perform classical method of solving such multi-objective optimization problem is to consider the multi-objective optimization problem but solve only for a single objective function at a time. Because the classical method involves solving for a single objective function only, so you take the multi-objective optimization problem, but you solve one by one, only single objective function of them. So thereby you do not consider the effect of the other objective function over a given objective function. And so, but in the real world, so you cannot neglect the other objective functions if they have a significant effect. So there lies the limitation of the classical method, that okay, if there is a dependency of one objective function over the other, so because you are neglecting rest of the objective function and their effect, and solving only one objective function at a time, so you may not get the correct optimal solution. So the other approach is by performing a weighted sum of the different objectives by grouping them into a single objective function. So another approach is that okay, you quantify the effect of each and every objective function, and you assign a certain weight to each objective functions, and then you perform weighted sum of the different objective functions to get a single master objective function, and then you solve for that master objective function. But again, this is not always the right way, because the weighted sum will not give you, because certain objective function may depend upon the rest of the objective function in an exponential fashion. So thereby, if you try to take a weighted sum, then you may not be able to accurately quantify for the effects of the different objective functions over a given objective function of the multi-objective optimization problem. So these are the approaches available, and there you can clearly see where the lacuna, or what is the hole in the approach is. So then now we have discussed the classical algorithm and their limitation and their approach. So now we can go and discuss that okay, what are the evolutionary algorithm advantages that are presented by the evolutionary algorithm, and why they are so well suited. So the evolutionary algorithms have recognized to be well suited for the multi-objective optimization problems because of their capability to evolve a set of non-dominated solution distributed along the Pareto front. So evolutionary algorithms are quite well suited because they can evolve over a set of non-dominated solution. So what are the non-dominated solutions? So non-dominated solution here means that okay, you have a set of solution which you cannot if you choose any one of the if you try to divert from such the solution to go over to choose over another solution, you might compromise or you might have to trade off with another objective function for one objective function. So those type of solutions are called as non-dominated solution. There is no other better solution other than that set of non-dominated solution. No other solution can dominate over them. So those are basically the optimal solutions available. So those are the set of optimal solution available for a set of objective functions, whereby if you choose one optimized solution over the another, you might observe a certain trade-off between given two or more objective functions along the Pareto front. Now so another advantage is their ability of an evolutionary algorithm, their ability of an evolutionary algorithm to find multiple optimal solution in one simulation run makes evolutionary algorithm unique in solving multi-objective optimization problem. So evolutionary algorithm, they on a single simulation, you do not, unlike the classical method where you have to manually solve for each objective function one by one. Here it considers the entire problem as a multi-objective optimization problem, and in a single simulation step, single simulation execution time itself, it solves for each and it considers and solves for each multi-objective function in a given optimization problem. So that is, so basically it considers the effect of the rest of the objective functions over a given objective function also. Now, evolutionary algorithm come in various forms such as the genetic algorithms, genetic programming, evolution strategy, and particle swarm optimization techniques. So let us start with the genetic algorithms. Just a minute. Okay, so yeah. So we were at genetic algorithms. So genetic algorithms are most popular optimization technique for the kind of strategies that are available among the evolutionary algorithms. It employs representative techniques of evolutionary strategies which are inspired by nature. In this algorithm, the decision variables are codified to constitute as a chromosome. Now, to solve a multi-objective optimization problem using genetic algorithms, there are various genetic algorithms available to solve multi-objective optimization problems. Those are vector evaluated genetic algorithm or VEGA, multi-objective genetic algorithm or MOGA, and non-dominated sorting genetic algorithm, and niched Pareto genetic algorithm NPGA. And again, instead of non-dominated sorting genetic algorithm, there is a part 2 of that, non-dominated sorting genetic algorithm 2 second generation, NSGA second generation, and microgenetic algorithm or MGA. So genetic algorithms, basically, because the evolutionary algorithms or the evolutionary methods are based upon rely upon the idea behind them is to basically the natural evolution, and genetic algorithms represent them on a very fundamental manner, that here in this algorithm the decision variables are codified to constitute a chromosome. Now, out of these six genetic algorithms, we would be looking at one of the most commonly used one and most very easy to implement, and the most commonly used one is the non-dominated sorting genetic algorithm of second generation. So, what is non-dominated sorting genetic algorithm second generation? It is a multi-objective genetic algorithm with low computational requirements. That is very efficient computational. That is very you can do that on a very low level system also, and it has an elitist approach and the parameter less sharing approach with respect to the first generation non-dominated sorting genetic algorithm. It is the most used multi-objective genetic algorithm and is usually taken as a reference algorithm when developing and testing new algorithms. This algorithm builds a population of competing individuals who are sorted according to the non-domination level. Then the algorithm applies evolutionary operations to create a new pool of offspring. So new pool of, instead of offspring in terms of mathematical, so new set of new set of potential solutions. It then combines the parent and the offspring before portioning the new combined pool into Pareto fronts. So this is how it performs. That okay, this algorithm will first build a population of competing individual, here potential solutions, who are sorted according to their non-domination level. Then they are sorted that okay, which out of these potential solution, who are the non-dominating optimal solution, that okay, there is no other better solution than those for given set of objective functions. Then the algorithm, so this sort of non-domination level are where non-dominating potential solution are called as offsprings. And then it combines the pool of the parents and the offspring, and then portion them that okay, these are the optimal solutions and this is the Pareto front of the given optimization problem. Now out of these mentioned 6 genetic algorithms, and out of these 6 we have discussed one, but there is another new algorithm that is inspired by nature like genetic algorithm, which are known as the meta-heuristic algorithms. Now a meta-heuristic algorithm is an algorithm designed to solve approximately a wide range of hard optimization problem without having to deeply adapt to each of those problems. Meta-heuristics are characterized because they are inspired by nature, using stochastic elements, and have various parameters that must be tuned for each problem. So there are 2 stages of meta-heuristic algorithm: diversification and exploitation stage. So there are 2 stages: diversification stage and exploitation stage. A meta-heuristic algorithm depends on appropriate balance between the diversification and exploitation stage. So the dependence of the meta-heuristic algorithm is a balance between both of these stages. The diversification stage allows you to, now what is diversification stage? The diversification stage allows you to explore a large part of the search space, while the exploitation stage concentrate the efforts on those areas the search space which are more promising. So this is how the meta-heuristic algorithm work. The diversification stage will allow you to explore over a large set of space, and then the exploitation stage will concentrate over the possible optimal area, the set of solution that can give you a optimal process. Now, if a meta-heuristic algorithm gives more weight to diversification, then you could not be close to a global optimum. So that is actually the trade-off between what it means to balance between those 2 diversification and exploitation stage is that okay, if you have a meta-heuristic algorithm that gives more weight to the diversification stage, then you will not be able to get a solution which is close to the global optimum. But again, if you give more weight to the exploitation stage, then you could fall into a local optimum. So yeah, that is the trade-off you have to deal with. Now the most popular and used meta-heuristics algorithm are available, that are simulated annealing meta-heuristic algorithm, taboo search meta-heuristics algorithm, differential evolution algorithm, ant colony algorithm, and particle swarm optimization algorithm. So these are the 5 algorithms that come under the meta-heuristics algorithm. We will be discussing each of those. Now the simulating annealing, we first start to discuss what is those. Simulated annealing is a optimization technique inspired by the process of annealing of metals, which involves treating metals in very high temperature. So in this process, first the metal is heated by raising the energy of the molecules and allowing them to move freely. Later on, a cooling process is performed which minimizes the energy of the particles by their accommodation in a crystalline structure. If the cooling is done very quickly, then an amorphous structure is obtained which leads to a higher energy state. So annealing process is heating the metal to very extreme high temperature and then slowly cooling them down such that the crystallization happens. So instead, if you quench the metal, if you quench the metal very quickly, you would get an amorphous structure which may not be very strong. So that is the idea behind that, using annealing technique, that okay, So Kirkpatrick, others, and Cerny others pointed out the analogy between the process and the optimization strategy. So what is the analogy between them? The objective function is represented by the energy of the particles, while the temperature and the cooling path are the act as the operators. Now, unlike the genetic algorithm, the simulated annealing does not use populations, but instead it uses only one solution. Thereby, acceptance of a new individual is based on probability value. So it solves for a given objective function, but without directly into taking account of the other objective function, but again as a probabilistic value. So then there are many other approaches of the simulated annealing algorithm also, that based upon what sort of averaging or what sort of probabilistic technique that you are using for the other objective functions. So many other authors have proposed different approaches to use simulated annealing for multi-objective problem, such as the L infinity by the Chebayev norm, and weighted sum of the probabilities for all objectives for a single solution and entire population by Zigzag and Jaskiewicz, and Pareto dominance by Nam and Park in 2000, and normalized aggregation function by Hansen in 1997. Now similarly, now let us so we have discussed the simulated annealing. Now what happens with the taboo search? So the taboo search algorithm was proposed by the Glover in 1986, and based on this algorithm, a unique solution is evolved through admissible movement that allow decreasing or increasing the objective decreasing or not the objective in case of minimization. In this case, remember that reverse movements are not allowed in order to falling in a local optima. So taboo search it will go on decreasing, but it will not allow you to search on an other direction, because to prevent you to fall into a local optima. So you will keep on searching among your variables, keep on searching the optimal solution among the variables for different multi-objective functions, but you will search them on only one direction, and that direction is not reversible, because to avoid falling in a local optima. Now to register the information about the optimal points, different memory array act as an operator. Now the main operators are three kind of operators are there that act as a memory arrays: the short term memory array, intermediate term memory array, and long term memory arrays. These memories register the information about a recently visited point, optimal or near optimal points, and explored region respectively. So the short term memory array will register the recently visited points and what are the corresponding solution for those recently visited points for the objective function. And then the intermediate term memory arrays will they register the optimal and near optimal points about the recently visited points. And then the long term will give you the entire of the explored region, what is the currently standing optimization point. So that is the taboo search done. Now comes to the ant colony. So ant colony optimization algorithm was developed by Marco Dorigo, and that was inspired by the colonies of the real ants. And in the real ant colonies, the ants secrete a chemical substance called as a pheromone, which is used to communicate between them. So ants communicate among them chemically. The ants tend to take the paths where large amounts of pheromones are present. So if you could consider a gradient, so the ant will follow where the gradient is highest. So from a computer science perspective, the ant colony is a multi-agent system where the low-level interactions between the single agents, artificial ants, result in a complex behavior of the entire ant colony. So because of the individual, if you take simple fundamental individual behavior of the individual ants or the individual agents, single agents, if you account for each of them correctly, what would happen is you would get a complex map, a complex behavior of the entire colony. Similarly, if you take the analogy, you will be able to model the entire system. So in this way, at the beginning of the searching process, all the ants are dispersed looking for food. As the optimization process progresses, the ants begin to follow a common path, the one with the higher levels of the pheromones. In the end, the whole colony follows the same path, which is the shortest. Several multi-objective approaches have been developed in order to use the ant colony for this kind of problems. That okay, after a certain computational execution time, you will be able to get the optimal solution probabilistically, that okay, this is going to be my optimal solution. Now the another one is the differential evolution algorithm. The differential evolution algorithm is a meta-heuristic algorithm proposed by Prince and Stone in 2005. It was originally developed for continuous optimization, sharing some similarities with the traditional evolutionary algorithms. It does not use binary encoding as a simple genetic algorithm. And also, it does not also use a probability density function to self-adapt its parameter as an evolution strategy. So there are two things to consider in the differential evolution algorithm, that okay, it does not use a probability density function to self-adapt, and also it does not use a binary encoding as a simple genetic algorithm. Now there are several variants of the differential evolution algorithm available based upon the depending on the type of the selection and the type of the recombination and the type of the mutation operators that are employed in the differential evolution algorithm. Now the last and final is the particle swarm optimization algorithm, and particle swarm optimization algorithm was proposed by Kenny and Eberhardt in 1995. This strategy is similar to the evolutionary algorithms. The performance is measured with a function similar to fitness function, and this approach introduces the use of the flying potential solution through hyperspace used to accelerate convergence. So these are the 5 of the meta-heuristic algorithms that we have discussed. Just a minute. Okay. Now, what are the process synthesis intensification algorithm? Now, the application of the process synthesis intensification framework requires the use of different algorithms. The algorithms are grouped into two sets. The set 1 algorithms correspond to the algorithms that are needed to decompose the problem from the largest scale, that is unit operation, to the smallest scale, that is of the phenomena level, fundamental phenomena level. And the set 2 algorithms correspond to those that are needed to aggregate from the smallest scale to largest scale. So set 1 will dissect the problem. So set 1, the algorithms coming under set 1, they dissect the problem into individual components from the largest scale to the smallest scale, and then form optimization for them for different by dissecting them. And then set 2 algorithms sort of correspond to those algorithms that instead of dissecting like in the set 1 algorithms, they will try to aggregate or combine each of those different separated scale problem into one, and then they will perform the optimization. So in the set 1, so the set 1 algorithms can be further divided into 3 subset algorithms, sub-algorithms. So the sub-algorithm 1.1 involves the transforming a base case flowsheet into a task-based flowsheet. So you will have a reference case or a base case flowsheet. Then you will basically the step 1 algorithm of the set 1 algorithms will convert those base reference case flowsheet into task-based flowsheet. Then the second subset of the set 1 algorithms involves the transformation of the task-based flowsheet into a phenomena-based flowsheet for the identification of phenomena-based blocks, PBBs. So that we have discussed in the previous week also. And then in the algorithm 1.3, or the third subset sub-algorithm of the set 1, the identification of desirable task and phenomena-based block search space to overcome process hotspots. So now the set 1 algorithms, for the application of the set 1 algorithms, the following problem definition is used. So the given is a base case is given in the set 1. So what happens in the set 1 we shall discuss now, that okay, in the set 1 algorithm you will be given a reference base case design and identified process hotspot. You will be readily given that this is the reference base case design and these are the hotspots that have that needs to be translated. So then it will be translated into as a design targets. There the algorithms they identify a set of desirable tasks and phenomena based blocks that will represent those individual tasks, those desirable tasks. Now the subset of the algorithm 1, the first algorithm 1.1, sub algorithm 1.1, they involve identifying each unit operation, and then after identifying each operation, then identifying of the then finding of the corresponding task from the database of the unit operation versus task, and then replace each unit operation by single or multiple tasks that are associated with that given unit operation to obtain a task based flow sheet. So it involves identifying, searching and replacing. So it involves identifying unit operation and then searching for the various tasks that make the unit operation, and then replacing the unit operation with the given constituting tasks. Then the sub algorithm 1.2, for that involves for each task find the corresponding phenomena based block from a database of the task versus phenomena based block, and then replace each task with their corresponding phenomena based blocks to obtain a phenomena based flow sheet. So in the first sub algorithm you were breaking down the unit operation to form a task based flow sheet. Then in the 1.2 sub algorithm, what you will do is from the task based flow sheet you will form a phenomena based flow sheet, phenomena based block flow sheet. Then in the sub algorithm 1.3, you will identify the algorithm will identify the alternative tasks and their corresponding phenomena based blocks from the identified hotspots, that is coming from a database of known hotspots, tasks, and their corresponding phenomena based block that are linked to properly ratio matrices and binary mixtures. Then it involves adding of these phenomena based blocks to the original list of the phenomena based blocks. So basically the 1.3 the sub algorithm 1.3 will involve what are the potentially available phenomena based blocks available. So there comes the process intensification, because process intensification is not only just that okay given phenomena based, it also involves identifying of the potentially helpful phenomena based block that can intensify the given process. So with this, the set 1 algorithms have been done. Now what happens to the algorithm 2? Now the set 2 of the algorithm, it consists of 6 number of sub algorithms, and we will be going through each one of them individually. So in the sub algorithm 2.1 involves the generation of feasible simultaneous phenomena based blocks using combination rules. And then in the second subset sub algorithm of the sub algorithm 2.2, it involves the generation of the task based superstructure for identifying feasible task based flow sheets. And then the sub algorithm 2.3, what it does is identification of feasible tasks to be performed. And the sub algorithm 2.4 involves the generation of basic structure. And then sub algorithm of the 2.5 involves the generation of task based flow sheet. And then the sub algorithm 2.6 involves the translation of the basic structures into unit operations. So as you can see, in the set 1 we were going from the unit operation based flow sheet to a phenomena based flow sheet, but here we are trying to combine the different phenomena based flow sheet to form a unit operation based flow sheet. So it involves 6 steps. Now again emphasizing on the sub algorithm 2.1. So to calculate the number of the possible simultaneous phenomena based block, it can be done using the following equation, where the number of simultaneous phenomena based block, maximum number of simultaneous phenomena based block is actually the summation where number of phenomena based block minus 1 factorial divided by the number of phenomena based block minus k minus 1 factorial k factorial plus 1, and summing up all of these, where NPB E means, and where the NPB max, this comes from NPB number of phenomena based block minus number of phenomena based blocks of the energy NPBE minus 1 minus NPBM, which represents the number of mixing phenomena based blocks, and minus 1 minus NPBD, which represents the number of phenomena of the number of dividing phenomena based blocks. Now again, so it is not just that okay you will calculate the what is the number of phenomena based block and you will combine them haphazardly. So you have got the numbers, but then how to combine them, how to combine the different phenomena which are feasible in nature. As also in the previous session we have seen that okay you cannot combine heating and cooling phenomena based block to make one simultaneous phenomena based block. Why? Because it is not thermodynamically feasible. So there are certain rules for that. So we will go through the rules, that okay some of the basic rules that are available are that okay for the mixture and mixing and contacting phenomena based block, the rule is that okay it performs the cooling of a stream, that okay mixing and contacting wherever it happens, the rule is that okay it should perform the cooling of a stream, and wherever the two phase mixing happen, what the rule is that okay mixing of a stream with two phases will happen, and so there will be only one inlet for each of these cases. and for wherever the mixing and reaction is happening, the rule is that okay, it will perform the reaction without an external source. So it does not need an external source, it should happen with only one. And wherever the phase contact and the phase transition is happening, so it performs the contact of two phases. And wherever the phase contact and the phase transition and also the phase separations are happening, the rule is that okay, the performing of the separation of two phases. Now another, again coming to the feasible simultaneous phenomena based building block is that okay, mixing, two phase mixing and process phase contact and phase transition, the rule is that okay, it performs the mixing of two phases. And wherever the mixing and the reaction and the contact and the phase contact happens, it performs the reaction with external energy source cooling. So there should be an external energy source cooling provided, and also the reaction will happen simultaneously. And for the case of mixing plus a reaction, mixing that is similar to the reaction and that is similar to the two-phase contact, mixing, two-phase mixing, phase contact, phase transition and phase separation, the rule is that it performs a reaction, phase creation and phase separation simultaneously. So these were now the set 2 algorithm, once again going through them, that okay, for the application of the set 2 algorithms, the following problem definition is used. So what will be given to you is a set of phenomena building blocks and set of design targets. Now the algorithm, set 2 algorithm, will identify and generate a feasible sustainable design that minimizes, eliminates process hotspots and satisfy the design targets. So again, in the step 1, we have identified that okay, what is the maximum number of the simultaneous phenomena based block that you can obtain. So from the total number of possible simultaneous phenomena based block, you have to, the algorithm will identify the feasible set of simultaneous phenomena based block using predefined simultaneous phenomena based building blocks and combination rules. So whatever the combination rules that you are feeding in predefined, so based upon that it will perform combination. But yeah, those feeding up is actually a thermodynamically feasible one, so there are different rules for that. Not all of the rules are man-made, so most of them are actually natural. So and simultaneous phenomena based building block is a predefined feasible simultaneous phenomena based block as is, or it can further be combined with other simultaneous phenomena based block building blocks for generating more simultaneous phenomena based blocks. Now steps of the what comes in the algorithm of the sub algorithm 2.2 is, there are two levels for that. The first level is to generate the task based superstructure, which involves identification of the minimum number of separation tasks that need to be performed and a sequence the task starting from all possible reaction tasks to the separation task. And the level 2 considers the merging of the adjacent reaction separation task and update the task based superstructure. And the step of the what comes in the algorithm sub algorithm 3.3 is the checking of the feasibility of the identified task through the mixture property analysis. And then in the sub algorithm of the 2.4, which involves the identification of the basic structures that are able to perform a task, and then list this task as a feasible task with the corresponding basic simultaneous phenomena based structures. And then in the algorithm 2.5, sub algorithm 2.5, what comes is to generate the task based flow sheet consisting of the basic simultaneous phenomena based structures, based block structures. Now in the algorithm sub algorithm 2.6, the idea is that okay, to use a database to translate the basic structures to task and then to unit operations. If the basic structure and its corresponding unit operation do not exist, then in principle a new unit operation is generated. The list of unit operations are then screened based on the phase identity of the feed stream. Then the selected feasible unit operations are highlighted in bold and in table. So what happens is, here in this the step of 2.6, here you will be able to observe the process intensification happening in a live, that okay, you will be able to generate a new unit operation. Now, why is the design of a new intensified unit so complex? In such cases, there are smaller physical. So, why the designing of an intensification is very complex in nature is because in such cases, the physical spaces are quite small, because generally whenever the study is happening, intensification study is happening, we most of the time it is all in the laboratory scale. The physical spaces are quite small and reduced operating condition, basically to keep in mind of the safety. So because you cannot exceed beyond a certain pressure and temperature and pressure limit, because it is not safe. So due to the reduced operating condition, because let us say if you want to study a blast furnace which is going to thousands of degrees Celsius, but you cannot perform the same study in an experimental in your lab. So then you will reduce your operating conditions such that you can perform the study, such that your equipments and the human can basically perform the study. So these reduced operating conditions are due to the existence of physical and reactive equilibria, or the incorporation of the technology, for example microwave or ultrasound. So again, it is not that okay, it's just reduction, it also involves the change, that okay, it might involve new type of technology like microwave or ultrasound that might never have been incorporated in a given intensified unit. So therefore, the modeling of these processes is more complex than the modeling of the traditional chemical processes. Therefore, the optimization strategies, especially the evolutionary algorithm, became an indispensable tool to reach the optimal design of the intensified processes, since complete models of the processes are not required. So again this point emphasizes that okay, the optimization strategy, especially the evolutionary algorithm, is an indispensable tool to reach optimal design of the intensified processes. So I will just quickly mention some of the application of the multi-objective evolutionary algorithms that have been applied. So for example, of the application, So for example, in the application of the catalytic membrane reactor for the production of methanol hydrogen, the evolutionary algorithm that have played an elitist non-dominated sorting genetic algorithm, NSGA second generation, along with a non-isothermal model can be used. Now, in the case of the usage of reactive distillation, both conventional and thermally coupled, they are both conventionally and thermally coupled for the production of biodiesel. Here, a multi-objective genetic algorithm with handling constraint in order to generate the Pareto front can be employed. Now, for the application in the optimization of transesterification reactive distillation column with thermal coupling, here the elitist non-dominated sorting genetic algorithm of the second generation can be employed along with the HYSYS process simulator. Now again, for the another application in the distillation with the reactor for the desulfurization process of the diesel, the competitive results between the total annual cost CO2 emission and the amount of sulfur compounds that the hydrodesulfurization processes are discharging can be analyzed. And for the application optimization technique application in the extractive thermally coupled sequences for the separation of ethane and carbon dioxide mixture, the optimization plays a role that the sequences can here be simultaneously optimized by the minimizing the total annual cost and maximizing the acid gas removal. And again, for the application in the hybrid distillation melt crystallization using thermally coupled distillation schemes, the optimization techniques can then give you the design and optimization. The design and optimization can be carried out in this case as a design rule, as using a design tool, a multi-objective genetic algorithm with restriction coupled with the process simulator of Aspen Plus. Now, for the application in performing the diesel production, performing the biodiesel production in a counter current reactive extraction column, the Aspen Custom Modeler ACM can be employed, which includes the multi-objective optimization of the hybrid separation using evolutionary algorithms. The hybrids now again in the application of the hybrid separation combining nanofiltration and distillation for the wide boring mixture, the optimization under uncertainty using multi-objective evolutionary algorithm for the design of this intensified separation alternative can be performed. The optimization of a biodiesel process or production of the production considering as raw material soybean oil. So the production of biodiesel but considering soybean oil as the raw material. Here the stochastic tool with the Super Pro designer can be employed to optimize three objectives: maximize the net profit, minimize volatile organic compound emissions, and maximize the number of chemical operators. So these were some of the examples. Now in the course, the sir has also discussed that synthesis of a reactive distillation column for a production of ethylene glycol. So this is a case study that professor has done. So this case study was actually published published as a paper by MER Sirik and Dayayo Gu in 1994. So the paper's name is actually Synthesis of Non-Equilibrium Reactive Distillation Processes by MINLP Optimization, where the MINLP stands for Mixed Integer Nonlinear Programming Optimization. So here the goal is to determine the optimal number of trays, hold up per tray, reflux ratio, condenser and reboiler duties, and feed tray location. The ethylene, if you see the reactions what are undergoing here, the ethylene glycol is produced from the reaction of the ethylene oxide and water, C2H4O plus H2O, that will give you C2H6O2, which is basically the ethylene glycol. So ethylene oxide is C2H4O and it reacts with the water to give you ethylene glycol. But then the produced ethylene glycol can further react with the raw material ethylene oxide to produce unwanted or the undesired product, diethylene glycol. So the produced ethylene glycol C2H6O2 can combine with the original ethylene oxide C2H4O to give you the diethylene glycol, which is C4H10O3, which is a byproduct which is undesirable. So so this is basically the goal of the paper is to basically determine the optimal number of trays, optimal number of hold up per tray, and optimal reflux ratio, and optimal condenser and reboiler duties and feed tray locations. So this is a very good paper, which is a very good case study for the optimization technique that has been applied to achieve process intensification by the reactive distillation. So so this paper basically discusses a mixed integer nonlinear programming model for synthesizing reactive distillation column when chemical reaction equilibrium cannot be assured. The mixed integer nonlinear programming model minimizes the total annual cost subject to a rigorous tray by tray model. The solution of this mixed integer nonlinear programming model yields the optimal number of trays, the optimal feed rates, the optimal feed tray location. The liquid hold up per tray, the reflux ratio, and the temperature and composition profiles within the column are optimized as well. The mixed linear integer nonlinear programming is solved using generalized Bender's decomposition, and technique is illustrated with the ethylene glycol synthesis. So they have taken an algorithm of the mixed integer nonlinear programming algorithm, and then they have applied to the reactive distillation for the ethylene glycol synthesis. And it is a very good paper, so you can go through it, and that is what sir has performed as a case study in the third lecture of this course of this week. Now the reasons for producing ethylene glycol via reactive distillation is, so again and again we have been discussing that why reactive distillation is a better, instead of separating the two unit operation of a reaction and distillation unit separately. So the reasons for producing the ethylene glycol via reactive distillation is the large differences in volatilities between the ethylene oxide and ethylene glycol will lead to a rapid separation of these two components in the reactive distillation column itself, thus improving the overall selectivity. The part of the heat required for this separation is obtained from the heat of the reaction, which allows the reduction of the energy costs. So again, here it is not just the reactive distillation is happening, but the heat that is required for the separation is obtained from the heat of the reaction, which is another a good way of utilizing. Instead of making the heat go waste, they are utilizing the heat of the reaction to perform the separation. The separation task itself requires a certain heat that is fulfilled by the heat of the reaction, so thus reducing the energy costs. The data required for this problem include you need basically 4 data: reaction data, vapor, liquid, because it is a reactive distillation, so you need the reaction data also, and also because this is a distillation, reactive distillation, there is distillation also involved, so you need vapor liquid equilibrium constants, so you need vapor liquid equilibria data, and also you need cost data, so basically you have the economics in check, and also you need the thermodynamic data for non-ideal vapor liquid equilibrium. So you will, because this is a real system, so you may not be able to get the ideal vapor liquid equilibria, so you may get 2 charts, you may get 2 data systems for ideal vapor liquid equilibria and non-ideal vapor liquid equilibria. So then after so these are the 4 data that 4 variables that can be taken, and then with these variables the objective function is made, which basically consists of minimizing. So basically it is a summation, it is a long equation which sums up the cost of raw material, which also takes account the feed rate of the material into a given tray, and the cost of steam and the cost of cooling water. So basically what I'm mentioning is these are all the things that you need to keep in account, keep in check, that okay, what are the variables I need to consider to make an objective function for a given chemical process. So you need to take account of the cost of the raw material, you need to take account of the feed rate of the material to a given tray, and you need to also account for the cost of the steam, you need to also account for the cost of the cooling water, and you need to also account for the condenser and the reboiler duties, and then there is also an analyzing factor involved, and then you need to also take into the cost of the install column shell, trays, reboiler and condenser units. So all of these will come into the objective function. So there in the paper itself, there are different formulas have been given, that okay, how different cost estimate have been made based upon some certain index, and what is the based upon the column diameter, height of the column, construction factor, and height of the tray. Similarly, the reboiler and the condenser investment costs are evaluated by the height of the tower and what is the flow rate to each of reboiler and condenser units. And then again, the height of the liquid in the tray, in a given tray, is evaluated as a function of the minimum tray spacing, and with the corresponding as a function of a corresponding volume also. and also with the column diameter. Now if you substitute all of these in the objective function, you will basically get the objective function as a function of the cost parameters that are basically the column model and the material balance, the energy balance, and overall balance of the given components. So then thereby you can solve for each of these things by plugging right equations. So many people, many experimentalists have given empirical expressions for each of those variable quantities of interest. So one can go through the literature to while designing a particular process and then optimizing for them, constructing an objective function out of it, and then forming a optimization study. Now what are the calculation procedures? The calculation procedures, so once you have made the objective function, once you have performed the once you have formulated the mathematical problem objective function for a given process, then comes what are the different calculation procedures. The calculation procedures are reported for solving non-linear equations that can be broadly divided into 4 categories: method using equation decomposition or tiering partitioning, and methods using relaxation techniques, methods incorporating Newton or quasi-Newton methods, homotopy, and continuation methods. So where the decomposition method allow for the identification of blocks which need the simultaneous solution and blocks which can then be solved sequentially. Meanwhile, the relaxation techniques involve the liquid phase composition are computed based on non-steady state material balances, which in subsequent iterations proceed towards the steady state solution. And the Newton and quasi-Newton methods, these methods converge quite quickly from the suitable starting initial guesses. And then the methods of the homotopy and continuation, the advantage of forcing the desired solution by tracking a homotopy curve regardless of the choice of the initial estimate. Out of all of these 4, the relaxation technique is relatively more suitably used, but the Newton or quasi-Newton methods converge quite quickly, so they are also quite frequently used. So this was all for this week. If you have any doubt, we can discuss for the next week, for the 6th week. If you have any doubt, we can discuss that in the next live session. So okay, thank you.